So now that you are so completely overwhelmed with taking derivatives using limits, we're going to talk about where you're not allowed to take a derivative. And we're going to do this very visually today and for a little while. So please remember, these are your two limit definitions for derivatives. I'm going to write these equal f prime. This is the notation we talked about yesterday in the video and if you were in class. That little prime means first derivative. So these would both find the first derivative of f at this value of a. Derivatives are limits. Derivatives are limits. Derivatives are limits. Derivatives are limits. So if we're talking about non-differentiability, then really what we're talking about is where do these limits not exist? So remember, before your test on Friday, that places where limits don't exist are places where your left and right limit don't match. So the first one's going to be pretty okay with, I think you're going to be fine with this. You're going to have, let me write it, non-differentiability in three places. The first one is any discontinuity. And there are three types of discontinuities. So any jump, any hole, any asymptote. You're not going to be able to take a limit there, or you're not going to be able to find a slope there because the function doesn't exist there. So that should make some sense. Your function doesn't exist, you can't hang out from it, right? All kinds of issues arise. The second place where you cannot take a derivative because the left and right limits don't match are places called corners or cusps. So for example, if I have a squiggle wiggle that's not very squiggly at all, but comes in with a very straight line and then curves like that, the slope, so this is my value a that I cannot take a derivative at, I can find these slopes. It's linear, they're probably going to be constant. But these slopes coming from this side are not going to be the same as these slopes coming from this side. So it's not that the limit of the function doesn't exist. It's that the slopes on either side of a are not the same. So the limit of this function exists. We can call this f of x. So the limit as x approaches a of f of x absolutely exists, but the derivative on either side of a is not going to be the same. So you can't take a derivative at a for that one. The last one is a situation where your function is trucking along just fine, but then it shoots vertical for just a second. And there are quite a few functions that do this. X to the 1/3 is my favorite example. So if I have x to the 1/3, this is not x to the 1/3 because it would sit at the origin, but that's fine. At this instant in time, right here, these tangent lines on this side are not the same as these tangent lines on this side. It goes to infinity. And infinity is not a number, so you cannot find the derivative when you go vertical. These are called vertical tangents. So you cannot take a derivative at a vertical tangent or a corner or a cusp or any discontinuity. All right, let's look at graphing these things. So this is a picture of a function that I'm going to call f, and our goal is going to be to sketch a graph of f prime. And it's a sketch, guys. This is not going to be, you're not going to be in a situation where you can sit and plot points and then connect the dots. These are just sketches. So this one is a familiar, friendly graph that you know. This is absolute value of x. So I like to start with this one because we're going to actually use values that you know to start. What is the slope of this line segment? Well, if it's just absolute value of x, then that line segment has a slope of -1. Which means that the function derivative, the value of the derivative of this function for this entire line segment is -1. At 0, it's a corner. But to the right of 0, these slopes are now 1. So this green graph here is a graph f prime. You just graph derivatives. You're graphing slope values. So I know I kind of missed one. It's not a big deal. And then at 0, it's an open circle because you cannot take the derivative at the corner. So this corner value is going to provide open 0 or open circles. To the left of 0 is slopes -1, to the right of 0 slopes are 1. I like to start with this one because these are actual values that you can find and you know for certainty. But then very quickly, I don't know what, I mean, I do know what this is because I wrote it, but you don't know what this is, and I don't want you to try to find out. That's not the point. The point is we're supposed to go through and analyze the tangent slopes of this curve. So here's the process I encourage you to follow. I want you to go find horizontal tangent. So I want you to go find places where the graph that you're given, which I'm going to call f of x again, so horizontal tangents on f. I want you to go find places where f of x levels off and its tangent is 0. So for example, it appears to level off right here. It also appears to level off down here. That's the 0 tangent. What that means is your derivative values at those two spots are 0. So I'm going to graph my derivative in green again, but it means I should have a value, I should have an x-intercept for my derivative graph at those horizontal tangents, one here. So I know that the function I'm about to graph has to hit those two dots. And those are the only two absolute certain dots I'm going to have. Everywhere else, you're just going to analyze. I'll write it down. You're going to analyze positive or negative slopes. Positive. So I'm going to read it left to right. This is my first chunk. Starts where it starts and it ends at that horizontal. It ends at that horizontal. So for that chunk, what kind of slopes does that graph have? What kind of slopes do its tangents have? I mean, you can mark them as you need to. This is a tangent line. This is a tangent line. I understand that they're decreasing. That's not the point. The point is that they have negative slopes, which means the graph that I draw needs to be negative, not that it needs to be decreasing. Those are different things. So I don't want to talk to you like you have tiny brains, but sometimes you have tiny brains. This is negative down here. Anything you graph below the axis is negative. This is positive up here. Sorry about your tiny brains. This kind of messes with your brains too. So I'm really not making fun of you this time. So these are all negative. So these are going to come from negative. That's all I know. I don't know if it comes from way down here. I mean, I kind of know it's not doing this because it's a very smooth curve. But all I need for today is that you know it's got negative slopes. I'm graphing below the axis. Next chunk. Next chunk goes, picks up where you left off, and then goes until your next horizontal tangent. There. This entire region has positive tangent slopes. So we are going to go draw in the positive region of our grid. I'm not going to shoot off to infinity because I know I need to come back down and hit this dot. So we can't shoot off to infinity. And these slopes don't look like they're getting drastically large. Let's just do like this. And then don't forget to come back down and hit the point that you know you have to go through. Your last one is for this chunk. And all of those tangent values are negative. So we need to be drawing in the negative part of our graph. I know that's like an explosion of rainbow math. So I'm going to erase everything that is not our answer. So I'm going to erase all these highlights to get them out of the way. I want you to understand only this green there, only this green graph is our answer. The question was to graph f prime. This green graph is a sketch of what I think the derivative function looks like. All right, I have two more. If you want to pause and try this one, I think that would be a good idea. There's nothing tricky here. I just made it a super squiggle wiggle. But when you're ready, first let's find all of our horizontals. I think I have one here. I think I have one here. I think I have one here, and try to line that up as best I can. So I'm finding the horizontals and I'm putting zeros on the derivative graph. So this is f, and this time I'm doing f prime in red. All right, so if I start over here to the left and I read this graph, these are very steep slopes, very steep, but very positive. So this must be coming from up here. Between these two horizontals, it's going negative, so we have to go. We have to be in the negative region, but go back through the point we know we have to go through. After that, these are positive slopes through here, so we have to graph in the positive region. Don't go too far because you got to come back down. From this horizontal to this horizontal, it's negative, and they look pretty steep. They don't look as steep as those, so I'll keep that in mind. And then it's got to level off so it can hit 0 again. I don't like how chunky that looks, so I'm going to do it again. And then we end with this last region shooting off positive slopes, so I'm going to draw a positive derivative like that. I have one more. Same thing, just one more. These mess with your head. If this is really twisting your brain around, it's okay. It always does. Okay. This one's kind of strange looking. If I go find my horizontals, I think I only have one. I think it's like here-ish. So I think I'll mark it here-ish. These aren't going to line up perfect, and that's okay. But do you see your cusp? So remember that at a cusp, you have no derivative. So I should not have a continuous derivative function this time because something's going to happen when I get to this x value. I don't know what yet. We'll talk about that in a second. But let me start on the left and work my way over. So if I start on the left and I'm looking at tangents, all of these tangent slopes are positive. They're not super steep, so they're not very positive. I should not come from up here because I'm not coming from like a slope of 6. These are pretty flat tangent lines. So I'm just going to come from down here. Make sure you hit the point you know you have to go through when you get 0, slope of 0. Then on the other side of that horizontal, the slopes are definitely going negative. But look how negative they go. So let me zoom in on that cusp. Look at those tangents. They are getting really, really, really steep. They're almost vertical. So what happens here, when I zoom out again, is these are going negative. They're going negative. They're going to negative infinity is what they're doing, which makes asymptote here. Anytime you approach infinity from a side, that's the definition of a vertical asymptote, and that's what's happening. And then watch on the other side. I zoom back in and I look at these tangent slopes, all positive, and look how steeply positive they are for a while. Means that this thing is coming from, let's see what this means, it's coming from positive infinity up here. And I don't know because I don't have a lot of graph to work with, but I know it's not doing this. I know it doesn't hit 0 again because I don't have another level off section. So I think I'm just going to do like this and try to stop my x values with the x values of the function. All right, that's how you sketch graphs of different functions. It's going to hurt you because you like things to be, like you want to sit there and plot points. You cannot plot points with this. You cannot do it. Please don't try. It will not work. You will be wrong. Okay, good luck. Let me know if you need anything.